we had a map of some hill, which was a grid with some positions blocked. And now we were considering going from upper left corner to the bottom right corner. And there were like and the height of the altitude of some position was like on which diagonal does it is it like positioned. So all those positions were on 0, all those positions were on 1, all those positions were on 2, and so on. So we were considering different people because for each person going there was some like different cost of going one step up and going one step down, and we were wondering, out of a big set of people, which was up to 500,000, who's the fastest one to get there, and how many such people are there. Okay, so the main observation here is that since we have this like altitude defined in that way, and let's say we have some path which goes up exactly x times, then I claim that it goes down exactly x minus m plus 2, I think, times, yeah. Okay, so who has any question to this claim? Okay, cool. So that means that there is like only one good path which we are actually interested in, and we'll apply the same path to like everybody. So we just run BFS to find this path, and then check like who's the fastest one. Any questions? Okay. So the next task. The next task is factories. Okay, so in this task we had some sequence. Yes, and what we are interested in, picking some intervals such that every negative number is inside some interval. This sum inside of every interval is non-negative, and also the intervals are disjoint, and we want to minimize the total length of all those intervals. And the length is 500,000. Any questions to the statement? Okay, so what we can do? Well, let's think about dynamic programming here. So. So basically, what we want to do is when we are considering, we can only consider non-zeros as the ends of the intervals, right? because there is no reason to, like, if 0 is here, we can just make it shorter, right? And the other way too. Okay, so we're gonna do the dynamic programming. dp n, which means what's the best cost that we can have. And when we fully solve the prefix n, okay. And now how do we calculate the next value? Okay, so when we are on some as I mentioned, we only care about those non-zero positions. So when we are on some non-zero position, what we wanna find is let's have some array of prefix sums already calculated. So because when considering the sum of some interval is prefix sum at I minus prefix sum at j minus 1. This is the sum on the interval from I to j, right? So we want this expression to be non-negative. So we want to find a prefix such that its sum is at least 0. So this part can be at most pi, right? And we want to find it with the best cost. So what we can see is that for each prefix, we basically, if we have some prefix sum with some fixed position, we only care about the furthest prefix sum with this position, right? Because the cost will be with this sum, because the cost will be better when we connect there. So we need to maintain some segment tree or set or whatever to get those maximas. Any questions? Okay. Okay, the next task is a number. So in this task we had to calculate the number of, let me check the limits. We defined a good number as a number for which every digit of this number is a divisor of the number. Okay. So, and we wanted to calculate the number of good numbers on some interval. R up to 10 to the power of 18. Okay. So the first thing is to, as usually in such tasks, we only need to be able to count on prefix. Right, and then count on the interval is the difference between two counts on a prefix. Okay, so we can do a digit dp here. Digit dp with where we need to maintain such information. dp. Okay, and to make it easier, instead of number of those which are smaller or equal than r, we will be calculating number of the ones that are smaller than r plus 1. It will be easier in NDP. So this is how many digits do we have? How many digits did we already consider? Did we already put? Here is 0, 1 flag. So we will be putting the digits from top to bottom. And this 0, 1 flag tells us if there was already a mismatch between r plus 1 and our number. Because like the tricky part here is that if we have this r plus 1, let's say it's 1, 0, 1, 1, 5, 3, then if we are like constructing our number and we put 1, 0, 0 here, then we like don't care what's there. There can be anything, right? But if we put 1 here, then it means that we still need to like obey those inequalities here, right? Because we cannot exceed this number. Yeah, and r plus 1, and like being strictly smaller than r plus 1 is better, because then we collect only, like in my opinion, is better in the implementation, because then we only like collect the result from the ones where there is 1, like in this. Okay, so we need to remember also that. We also need to remember so smaller 0. Okay, so the thing is that in this task we cannot put 0 in the middle of a number, but we can on the top. So we can have additional flag which tells us did we already put any maybe non-zero. Okay, and then let L equal LCM 9. So here we have this dimension is L, and here we will maintain like number modulo L. And we also need to have a mask of digits which are already used. So this is like 2 to the power of we can do to the power of 8 because we don't care about. Okay, let's think for a second. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so I think we don't need 1 because it doesn't change anything, and we don't need 6 because we can say that like 6 is at 1, 3, right? Because we don't really need to know the whole set of digits. We only need to know for which like divisibilities do we need to check. And being divisible by 6 is equivalent to being divisible by both 2 and 3. Okay, we could in theory optimize it further. So for example, instead of like having a separate bit for 2, 4, and 8, we could have like 2 bits which are like 0, 2, 4, 8, and then they say like which power of 2 do we care about? Yeah, but I think it's not required, right? Yeah. Okay. Yeah. So, are there any questions to the transitions in this DP, or like how do we get the answer? Yes.
You're saying you don't need a 6 for the rest?
Yeah. So like, okay, because maybe why do we even need to store this? So so why do we store number modulo L? Because if we there is a property that like x modulo PQ modulo Q is equal to just x modulo Q, right? So like, if we have some number modulo something and then modulo it by a divisor of a modulo, we get something like that. Okay, cool. So that means that we are able to get L modulo any digit, right? That's why we store, this number modulo any digit. That's why we store it modulo L. Okay, cool. And now, like putting some digits, when we in some like at some moment decide to put a digit 7, it means that our outcome has to be divisible by 7, right? So that's why we store the mask here to remember what set of requirements is there. So we do not need to store a requirement. It has to be divisible by 6 because we can say it has to be divisible by 2 and 3, right?
Yes, sir.
Okay. Any more questions? Okay. Can I erase that or anybody? Okay. Okay, so next problem will be virus, and I'm really like puzzled what happened here. It was intended to be like one of the easiest tasks. Okay, so the statement is that we have a sequence of zeros and ones. Okay, and on each day we can block some 0, and then what happens between the days is that every 0 that had a neighboring 1 transforms into 1. Except the zeros which were like blocked. And we want to like with this blocking we want to make because like at some point it stabilizes, right? After n rounds there is nothing more going on, and we want to maximize the number of zeros which stay as zeros at the end. Okay, so so basically what we only care about is the set of the it's like the sequence of the lengths of the intervals from the inside, right? Like it does not matter for an answer if input is this or this, right? Provided that those intervals are like fully inside, because then there are like ones because this is the same as this, but it is not the same as this, because here there is like no 1 going from left and eating this sequence of zeros, but otherwise only like the multiset matters. Okay, so who agrees with this statement? Any questions to this? Okay, and my second claim is that we will be like saving those. What we will basically do is we will in order from the like let's ignore the border ones for now. So what we will do is for in order of length for those intervals of zeros, we will be saving them. And what I mean by saving, we will block one end, and then on the next day we'll block another end. And it's like some simple inequality to see that like I'm not gonna do it on whiteboard, but I will tell like what to do if somebody is really interested in a proof. So we can like prove that if there are two intervals and we are doing something like block here, block here, block here, block here, then by like exchanging those two blocks, we do not decrease the score. And in that way we can prove, and also like the same argument applies to the lengths, so that like if we start with a shorter than longer, if we exchange those two, the score will not decrease. Okay, so that like solves our problem for all the for all the like ones which are inside. Okay, what do we do with border ones? So the model solution had some greedy claim about them, but it is possible to not do any greedy claim, like not do any more greedy claims here. So we'll do a DP. Okay, so DPN0101, which means what's the like best number of zeros that are saved when we consider first and middle intervals. We already considered the left border interval. We already considered right border interval, right? So in this way, we are basically like considering all the ways to put those two border intervals inside our pipeline of like blocking those middle intervals, right? Who like agrees with this statement? Okay, who has any question to this statement? Maybe I should repeat something or. Okay, so
I have a question.
yeah.
The previous statement in which you said that if you exchange the order in which you solve the intervals does not affect the score. It also applies when the intervals are too small to survive 4 turns.
Yes.
Steps. It always applies.
Yes.
Okay.
For the middle intervals.
Yes, for the middle. Yes.
Because like the like intuitive argument here, okay, we don't care that this guy does not survive. We will have like at least that many more in this first guy. That's basically what you get when you like write down all those inequalities. Any more questions to this? Okay, so like one thing here which really surprised me is like not only the fact that like okay, like I get it that sometimes greedy problems are way harder than they look, but I'm really surprised why there were so many teams with like -6 or -10. So like my advice here is to write a brute force solution and test generator. Like when you see you are already -3 on some task, and then like how to write a brute force. Okay, who immediately sees how to write a brute force solution here? Like let it be exponential, whatever. Yeah, so like the simplest brute force solution here is it works in like n factorial times n square. How do we do that? We choose a permutation and try to block in exactly this permutation, right? And okay, this is like not the fastest one. So how can we optimize it further? We can say that we only can block zeros, right? Like we only put onto the list of the positions which we can block the positions which are zeros at the beginning, right? Then it's a bit faster, or we can do even faster. We can do like backtracking over which one do we block, right? And I'm pretty sure that such like a brute force with a generator would find like at least half of wrong answers before even submitting. So my advice is to like once you see that you are getting wrong answers on some problem, and it is not hard to come up with a brute force, because sometimes sometimes answer is a rational number. I mean any rational number, or like any real number. Then yeah, then it might be hard to write a brute force solution. But in such a task, I really believe you will get like both less penalty and faster like feedback loop, because okay, so maybe how many teams did write such a brute force? Crazy. Okay, so like I'm not only talking about getting better penalty, because it's one thing here, but I also think it gives you a faster feedback loop because you immediately get a test on which your solution doesn't work, right? So like you can verify then your claims and fix the thing that does not work, right? Okay, so maybe like who heard about writing a brute force and a generator before? Okay. Yeah, so that's all that I can say here. I've just noticed that, like, for example, on this camp there are way many like wrong answers than I expected there to be. Like when, for example, when you look at standings of some competitions, you rarely see more than few -5s, and I think that's for a reason. Okay, so. Any questions to this part? Okay. Okay, so next task will be areas. Okay, so in areas, we had we are considering a sphere, and like we are considering a geometry of a sphere, and there are n rectangles. And the thing is that for each of those rectangles, we only know 2 corners of a rectangle, right? But the problem is that on a sphere, it does not determine which a rectangle is it, because there are 4 of them. So what we want to do is for each of those rectangles, we want to for each of those descriptions of rectangles by 2 corners, we want to decide which rectangle is it out of the 4 possible. And we want to do it in a way so so the area of the intersection is the biggest achievable, and n is up to 100,000. Okay, so who understands the statement?
Is it the union or the intersection of the areas?
Intersection, I'm pretty sure. Yeah, okay. Any questions to the statement? Okay. So first thing that we want to do here. Let's think for a second. How do all those 4 possible rectangles look like? So let me draw them. Okay, so the first observation is that union of all of our choices covers the whole sphere. That's the first thing, and the second thing is that there are more or less we can say that there are 2 independent choices, and so one choice is in the x-axis. And second choice is in the y-axis. Okay, so who understands what I said? Okay, so maybe any questions to? Yes.
What do you mean there are two independent choices?
Okay, so
I think it's easier to explain it. Like for each dimension, you're choosing if you go
oh yeah, okay.
inside or outside.
Yeah. So like for the x dimension, you can choose if you wanna go there or you wanna go there, right? And independently, for the y dimension, you can choose if you wanna go there or you wanna go there, right? Okay, and thanks to this independence of the choices, like we can also see that that like if we pick some of those rectangles, the answer like if we already have the rectangles picked, then for like let's say we are on a normal plane for a second, then the area of the intersection of many rectangles is area of the like x-axis intersection. So like we are projecting all the rectangles onto an x-axis and take the intersection of the intervals, and then we are projecting onto y-axis and take the intersection there. And on the normal plane, it's a product of those lengths, right? Okay. Any questions to my statement? Should I repeat or? Okay, so it also holds on sphere. Cool. So what we're gonna do now is we want to just solve it independently for both of the dimensions. Okay, so how does the problem on one dimension look like? We have a segment, and we want to choose if we prefer this or this. And then we have another segment, and we have to choose if we prefer this or this. Yeah. Okay, so the important thing, like what makes the solution work, is that for every choice, the sum of the choices is the whole interval. So that means that that means that every like point, every position belongs to some valid choice, right? Okay, so now we want to assign a unique identifier. So like, what we could do if we didn't care about the solution at all, we could for every point calculate the set of the choices and take the and the result is the set which happened, which like appeared the most often, right? Any questions to this claim? Okay, so how do we do that if we care about the complexity? So we are going to use the property that's of this, like the sum is always the whole segment now, because it implies that we do not need to check if there are n elements in a set, right? Because if there were like empty points, if we could not choose something, right, then we would have to filter those sets for those who only have exactly n elements inside, right? Okay, so what we can do is let's pick a random number for every choice, and at a single position, let's assign a hash of the choice to be sum of those random numbers. Okay, and then like my claim is that the answer is just the most popular sum. Who sees that it works for? Okay, so like let's ignore the fact that there might be a collision. Okay, who sees that it works? Who has some question maybe? Yes.
I may want to, hear back
Okay.
the part of, taking the sum from every point.
Okay, so once more. Let's assign some numbers to the choices. So here, this is 1, this is 2, this is 1, because this is the same choice, right? This is 3, this is 4, this is 3, right? Okay, so there are like segments of length 1, and for each segment of length 1, we see what set of choices do we need to like pick to get it, okay? So here you get set 1, 3. Here you also get set 1, 3, right? Here you get set 4, 2. Here you get set 3, 2, right? And like my claim is that we want to take the longest, like we want to pick some choices such that the intersection of everything is the longest possible. So my claim is that the result is the most popular set, right? That's any question to this claim? Okay. And now, since we know that, we want to, okay, so we know that there is no like empty position somewhere, on every choice it covers the whole line, so it means that every set here is a valid set of choices, right? And it contains n elements, if there are n like choices to be taken. Okay. So what we're gonna do is instead of calculating those sets explicitly, we want to calculate hashes of those sets. So the thing is just to like, instead of assigning the IDs from 1 to n, let's assign the IDs at random. Okay? And okay, who intuitively sees that, oh, it's unlikely to have a collision if we assign like totally random. Okay, but who's able to believe that? Maybe I should ask. Okay, who is not likely to believe this claim? Okay, so you are not likely to believe this claim. Okay, so basically there is a lemma called, I think, Schwarz-Zeppel lemma, which says that like if we have some multivariate polynomials and we want to compare them for equality, it is sufficient to evaluate them at random points in many times. So our multivariate polynomial here is we have a separate variable for each choice, right? And like assigning random values at random is basically evaluating at a like random set of points, right?
How many times do you need to?
Okay, so the Schwarz-Zeppel lemma gives us a bound that like if we are operating in ZP, so like we are doing everything modulo P, and the like size of everything is n, then then if they are different, we will fail with the probability at most n divided by p. So if the modulo is 10 to the power of 18, then like whatever, we are safe, right? This also is used to prove the like polynomial hashing, right? Because we also have polynomials there, but of one variable, not of multiple variables, and it also like tells you why. I mean, it does not imply, but like. You see that like if you have a modulo 10 to the power of 9 and you do a million comparisons of string hashes modulo, then this probability like it only guarantees that we not fail with a probability like 999 divided. So like there is 1,000th probability of failure, which happens, right? If there are like sufficiently many comparisons. Yeah. So this is basically the way to hash sets. It is very useful in general. Like you sometimes have this problem in some tasks that like you just have to compare two big sets, and you want to support like multi-sets, and you want to support insertion and deletion, you can do exactly that, right? Because like insertion is just one addition modulo, and deletion is just one subtraction modulo. We can also easily merge two multi-sets by just adding them, right? Okay. And back to the task. So we like just calculate this on one axis, on the second axis, multiply, and it's our result. Okay. So I will talk a bit more about those hashes because there are a few interesting things there.
Question? Don't
Yeah.
we run into the birthday paradox in here?
No, 10 to the power of 18 is enough.
Oh, okay.
But yeah, but like it's a good point that whenever we are like looking for two similar, whenever we are looking for two exact things. Okay, who heard about birthday paradox before? Okay, so not everybody. So I'm gonna talk about it. So the classic thing to start such a like talk is two people in this room have birthday on the same day. Who believes that statement? Wow, more people than the people who heard about birthday paradox believe this statement. That's interesting. Okay, but like, what's the? I can even say the like stronger statement. Only like among people in first 3 rows, there are 2 people with the same birthday. Who believes this statement? Okay, who would have believed this statement if I didn't mention birthday paradox or probabilities at all? Okay, the set is different. Cool. Okay. So the name of a birthday paradox is like the question is how many people do we need to have a 50% probability that 2 of them have birthday on the same day? Where we're like we consider the distribution of the birthday days uniform, which is not true, by the way, and we are picking people at random. Okay, so it seems that there are 365 days in a year, so we'll need roughly that, maybe half if you want the probability to be half. But it turns out that the answer is, I think, 20 something. It's for big N, it's roughly square root of N. Okay, so I'm not gonna to write a detailed proof, but I'm gonna to give you a quick intuition about it. So what you can think about is of the like number of implicit comparisons, because like what you are probably thinking about is, okay, let's pick 2 random people. What's the probability that their birthday day matches? Okay, so it's 1 divided by 365, right? Okay, but if we pick n people, then if we pick k people, then implicitly we do k choose 2 comparisons, right? Because there are like everybody is being compared with everybody, so that's why we need like square root, right? Okay, any questions to that? Okay, and this is both cool and not cool in competitive programming. So why is it not cool? Because in tasks where like we need to calculate some hashes and count the number of distinct elements, there is a higher probability that we will fail than we sometimes think about it. So that's why we need big modulo like 10 to the power of 18 to get things right. And it is cool because sometimes there are problems which require us to find something that this, for example, means that if we have a set of a if we want to, okay, maybe never mind. But like, sometimes there are problems. I cannot like think of a problem right now. But I remember seeing quite a few where you need to construct some object modulo, and the answer is to like, and thanks to a birthday paradox, we only need to consider like square root of objects. Okay, and one more thing with this caching. So there is like, I know how popular is this method, but some people claim that, oh, but like we don't need to do random. Let's keep like sum over AI, sum over square of AI, sum over cubes of AI, sum over fourth power of AIs. And how do you construct a counter test here? Like I heard something like that on a lecture, that like you should use that. And I'm saying, no, you should not use that. And why? Okay, so let's consider two sets. One set is S0 is the numbers. Let's pick some k. X is like from 0 to 2 to the power of k. Pop count x is equal to 1 modulo 2, 0. Okay, so let's pick two sets. First set is all the k-bit numbers with even pop count, and second is like the ones with odd pop count. Okay, so the funny thing is, it has like those two sets have equal sum of second power, sum of third powers, up to the k minus 1. So this is just like helpless. Like I even know a task which like required you to maintain some kind of sums and use this as like some of the test cases to screw up this. So like never do this. It's not gonna work. Any questions? Okay. Okay, so now let's talk about bits. So in bits we have n integers, a1, a2, an, and we are asked to find the sequence b1, b2, bn, such that the sequence is bounded by 0 and m, and sum bi times pop count ai is as big as we can, and AIs can be negative, and n is up to 600 if I remember correctly. No, 200. My bad. Okay, so who understands the statement?
Right.
Yeah.
I think you swapped pop count of BI with AI.
You are right. Thanks. Okay. Any questions to the statement? Okay. So like our first observation here is, let's think about this sequence be something. So it's a sequence of strictly decreasing, it's a strictly increasing sequence, here we are like dealing with bits of this sequence. So we might think about like how do those BIs look like when we write their like binary representations next to each other. So thing is that if we consider the topmost bit, then some prefix will be zeros and some suffix will be ones. Who agrees with this statement? Who has any question to this statement? Yes?
Why must the prefix of zeros and a suffix of ones? Can't you have it mixed?
It's a sequence of increasing numbers, and this is the topmost bit. Right? So that means that, like, if you had 0, 1, 0, something, something, 1, something, something, then this number is for sure bigger than this number, right? Because it's a binary representation. So the highest bit is bigger than the sum of all the others, right? Yes. So if this sequence is to be increasing, then this condition must hold.
Okay.
Okay? Any more questions to this statement? Okay, cool. So, so what we actually, and why do we care about this? Because when we look at our like scoring function with a pop count, this means that like we can already see the contribution of those bits to the pop count, right? To the result. So when we decide to do something like that, then what happens is we need to solve a sub-problem. So on this, we want to we want to solve it on this interval with like bound equal to this was, let's say this was like m. So here we have a bound m minus 2 to the power of k, right? Like without the highest bit, and here we also have an upper bound. Yes. Here we also have an upper bound of m minus 2 to the power of k, right? Who sees that? That like we are basically we will basically have two independent problems here. Okay, so questions? Yes.
Isn't the bound on the left just due to the table?
Okay, sorry, you're right. Yes, you're right. Sorry. And okay, so let's keep those bounds strict. So yeah, so now we have like a strict bound of 2 to the power of k here, and a strict bound of m minus. Okay, yeah. So here is the thing that like we need to somehow know if like the bound on the right is like because we need to maintain this the monotonicity, the strict monotonicity of the sequence. Okay. So what we need to also maintain is because we will be doing like some kind of dynamic programming here. We want to be able for every sub-interval to have the result with like some bounds, right? But what we can see is that those bounds are either powers of 2 or like bit prefixes of n, right? Who sees that claim? Because like the thing is that m is up to 10 to the power of 18, so it would be bad if there were many possible bounds, right? But what I'm saying here is that like the only bound we are ever going to have, because here like we say we have some recursive function which like computes the result for a subinterval, and what we're gonna do is we're gonna try all the splits, right, with zeros and ones, and so it will be like max over let's say we are computing it for LR, max over so sum from I to R times this is like the contribution of those ones to the pop count here. This is like sum over the AI sequence plus F L I plus F I plus 1 R with some updated bounds here, right? That will be our like result. So like we will need to maintain calculate the information for every interval, but we are fine with that. Like n is up to 200, and we also need to like think about what bounds are ever achievable here. So like what bounds will we ever demand from this recursion? So my claim is that like all those bounds are either like because we are starting with m as a bound, so let's write this m. So when we set this like where ones should be, then this becomes a new bound for a right side, and for a left side some power of 2 becomes a bound. So is it true? Yes. So what I'm saying, we have only like 2 log m possible bounds, right? Which is like 100 something. Yeah. Okay. Any questions? Yes.
Yeah, like I didn't get like the reduction you did from the original statement. Like how did you separate it into left and right?
Okay. So in the original statement, we need to pick this sequence, and yeah. Okay. So let's think about the fact that like this sequence exists, so its highest bit exists too, right? So let's iterate over descriptions of the sequence of highest bits, because it exists, so it has a description. So we saw that all the possible descriptions are of this form, right? Prefix of zeros and suffix of ones. Okay, so let's say we did some choice like that. So this like the fact that we did this choice adds to the result sum of AIs on this interval, because this increases pop count by 1 here. And now, what we need to choose is we need to choose all the like other things, right? So we see that we can choose whatever sequence we want here, but it has to have like smallest amount. It has to be smaller than this number, right? So it has to be smaller than like one. This has to be smaller than 1, 0, 0, 0, 0, 0, 0, 0, because we agreed that here is a bit 0, right? So like, okay, and whatever choice we do here has to be smallest than m minus 2 to the power of k, because like we are choosing only those lower bits here, right? Okay, and like so for one choice of the description of highest bits, we can like there exists a most suitable choice of everything else, right? So we are iterating over all the choices of this, and for each one we pick the most suitable choice, right? And then just take the best, right? Like dynamic programming. Okay. Any further questions here? Okay, 9:43. Okay, so I think we're gonna have coffee break like what time? Roughly now. I will just tell one more thing before the break. Okay, so let's say we have a sequence of the elements. Let's do not like think what those elements are. We have some operation star, which is associative, and that's it. Something like that holds, and nothing else. And we also have n queries, where each query is li ri, and we want for like this query to answer with so like basically we want to apply this commutative operation on the whole interval and answer with that. Okay? Okay, so like now my question is, and there are n elements and n queries. And we can do like arbitrary preprocessing, but it also counts to our complexity. And like how fast can we do that? That's the question for the coffee break. Yeah, yes?
In log?
Sure, we can do a log, but it is possible to do way faster.
Can we do like prefixes?
No, because like invertibility is not guaranteed. Okay, so any questions to the problem statement? Okay, so like let's do a coffee break here and discuss this after the coffee break. Okay, so did anybody come up? So before the break, we heard that there is like an log n solution to that. Like, I would expect everybody here to know the segment tree. So who knows something faster? Okay, what's your complexity?
My complexity is n log n.
Okay, I agree. Such solution exists. Do you have anything faster or? Okay, so who has something faster? Okay, you. What's your complexity? That's interesting. No, but like, you mean and okay? How do you do n?
Square competition
Okay.
for for 2 blocks, pre-calculate the solution in this range.
Okay.
And for each query, use this interval of blocks and one suffix and one prefix of two extra blocks.
Okay, but like, what if the query fits in your security block? Then what do you do?
What?
Like, you divide it into some blocks of length square root, right?
Six.
What if the query is here? Okay, I'm assuming nothing. Okay, so who has something faster than this? I'm gonna raise my hand. Okay, so actually we can do n log star n. Who knows what it even means? Okay, so it means how many times do we need to iterate a logarithm to get 1? So like, if you have 2 to the power of 2 to the power of 1024. Then when you take a logarithm of that, then we have 2 to the power of 1024. When you take another logarithm, we get, so it's like, here is 1 logarithm, 2 logarithms. When you take third logarithm, we get 1024. When you get next logarithm, it's 10. Then it's 3 and 1. So for this number, iterated logarithm is 6. Okay, so now how to do that? Okay, maybe let's explain this log-log solution first. So for this log-log solution, we take our sequence, we divide it into blocks of length square root, and for each block, what we want to calculate is all the prefixes and all the suffixes, and also we will calculate like the result for whole block, and on the sequence of the results for the whole blocks, we'll also calculate answer for every interval. So now, if our query intersects with at least one vertical bar, then we can it's some segment of some segment here and some suffix here and some prefix here, right? So we can answer constant time. Who like has a question to that? Okay, cool. What if it does not? Then, like to support the queries which do not, what we can do is we can run the same algorithm on those intervals of length square root and iterate this till we reach length 1. Yeah, and what's the depth of this recursion? So we can see that when we take a square root, then the logarithm of a value decreases by half. So, and logarithm can decrease by half only log times, right? So this preprocessing is log n log n. And now one can do some trickery here to have constant time answers, but like it's not required because we in this task because we do we also count preprocessing time into our complexity, so we won't be better than n log here anyway. Okay, cool. So how do we improve that? So we're gonna do something very similar. But instead, we're gonna do segments of length logarithm. And what can we do now? Okay, so now we can build. Let's for every element for every element here. Sorry, for every segment of length logarithm, just calculate the result. And now let's do a divide and conquer on this sequence. So yes.
I don't think I got the idea of
the previous one
example. Like you're calculating the prefix and suffix only for each block.
Okay, so what I'm calculating once again, I'm calculating the result for each block. So the result of the whole block, the result on every interval of blocks. So there is square roots. Choose 2 of those intervals of blocks, right? And for each block, prefix and suffix.
Okay.
So now every segment intersecting with a bar can be answered constant time in this, right? Because it's some prefix, suffix, and intervals. And for all who do not, I built another structure. I built I call this build function recursively in every block, and I'm iterating till blocks are of size 1, because then only query of size 1 can fit there, right? Is it understandable now, or should I?
Yeah.
Okay. So what we're gonna do now here is we're gonna do a divide and conquer on this sequence. When we have some sequence, we split it in half, calculate all the prefixes this way, all the prefixes this way, and iterate this divide and conquer further. So okay, what's the time complexity of that? It's n divided by log n, because blocks are of size log, times log n, right? So this processing is linear right now. And we also calculate all the prefixes and suffixes inside each log block. Okay, so my claim now is that we can easily provided that we can find if we have some query which intersects at least one vertical bar here, so it does not fully fit into this subsegment of size log, then if we are able to find appropriate vertical bar here, we can answer the query, right? Because when it intersects with this, that means that this is some interval of those log blocks, and we can take the answer from here doing prefix merging 2 prefixes, and then we need to also take some suffix of some log block and some prefix of some log block, right? And we can call this recurse into every block of size log to build the same structure for every log-sized block. to get this complexity, right? So now, like, the only tricky part is answering in constant time with this structure, right? Okay, so now let's think about it. So it's the same, like similar thing was on a first day with the brackets. So what we can do, we can for each like position note the time when it was a middle. So like let's. So here it's 0. Here it's like 1, 1, 2, 2, 2, 2. So basically, for some like query, we need to do a range minimum query on this to know the depth, and like range minimum query can be done with linear preprocessing and constant time answers, right? It's a well-known academic algorithm, I would say. Okay, if you don't know that, Google that. It's a fun task, but like it's useless on competitions because it has bad constant factor. But I think it's worth to know this. Yeah. So thanks to that, we can in constant time recover the like split position, and with that, it's like easy to answer everything else. Okay. Any questions?
Okay. Is the last algorithm useful in competitions? Because you mentioned that it has, or like, does it have a bad constant factor?
Like this whole setup is insane. It has super bad constant factor. Like whatever, it won't be faster than this in reality. And I think this is also useless. Like I think in most competitions, the only thing you really care about is like maybe sparse table preprocessing and constant time answers, because like sometimes you have like 100k length of something, but you do a bin search, so you get like 100k times log queries to a RMQ. So then like this sparse table actually saves our complexity, right? But otherwise, nah, it's all useless in competitions. Okay, any more questions? Okay. So let's go back to the problems. Okay, so let's start with task named Solve Me First, which got 0 solutions during the contest. Okay, so the statement was we have 2 numbers written in a Fibonacci system, which means that like they are a sum of written as a sum of Fibonacci numbers, and we get indices of those Fibonacci numbers which are in the sum. And also the notation is standard notation, so there is no like AI plus AI plus 1. So so like it means that everywhere there is there is at most 1 in every position, right? And also no 2 consecutive numbers are there, because they also mean some like next. This sum is equal to just the next Fibonacci number, so like this representation is just unique. Okay, and what we wanna, and the descriptions are of length 100k. So what we wanna do is to we wanna take a product of those 2 big numbers and also print their Fibonacci representation. Okay, so the first thing that's like that's concerning here is that we need to do the product of 2 big numbers, which basically screams FFT. I mean, like multiplying big integers is roughly always means FFT. There are like other algorithms, but yeah, in this problem we will use FFT. Okay, so who ever heard of Binet's formula for Fibonacci numbers? Okay, so there is for some number t, which is I think it's this value, but I don't remember for sure. It's like a golden ratio number. So it holds that nth Fibonacci number is t to the power of n minus t to the power of minus n divided by square root of 5.
Is +1.
+1, yeah.
Here?
No,
Here. Isn't it that like the 1 is +1 and the inverse is -1, so...
No,
Yes,
you
it's
change the square root.
Right.
Okay. So
It's not.
what?
No, it's okay.
It's okay now. Okay, we don't care. Like it won't be useful in this task. Like this part will be. Yeah. So, okay. What does it mean? It means that we can write our like. Let's represent our number as sum of powers of t's. Okay, so like we have the number a1, a2, and it's some fi, where I is over some set. So this means it's 1 divided by square root of 5. T to the power of I minus t to the power of minus I. Right? Is this like transition clear? Okay. So what we wanna, and here it's I goes over SA, and here I goes over SB. T to the power of I minus t to the power of minus I, 1 divided by square root of 5. Right? So what we want to do is we want to calculate a1 times a2, which is 1 divided by 5, sum I over Si, j over Sb, ti minus t. Like here, because like t is some number, but we will abstract it out, and we will say, for us, t is a variable. So like, we are basically doing something more general, but it helps for calculations, because we do not have infinite precision. We cannot store like sum of big numbers, so we are gonna represent this t as a like variable of a polynomial. Okay, this. Okay, let's maybe not do that here. So basically, when we unroll this sum, it says that A is some kind of polynomial. I mean, it's like a polynomial with also negative exponents, right? And and A2 is also such a polynomial. So we can calculate the product of those polynomials using FFT, right? I mean, negative exponents do not really hurt us, because we can like just increase it by n and then like decrease by 2n after convolving. Okay, so also like another thing here is what we can like notice is that this polynomial, because what's concerning is that, oh, but are we sure that we will be able to go back to like some of those Fibonacci's when we have just some coefficients, right? Because here we had those two paired, right? There's exactly the same amount of this guy and this guy. So yeah, we will. And why? So like those polynomials are palindromes, right? So like the product of two palindrome polynomials is also a palindrome polynomial. Yeah. Okay. So after calculating this product, we go into some like representation, but we have a problem that those conditions do not necessarily hold. So how do we fix it? I know is the team who accepted this problem there, like who solved this problem there? Okay, because like I looked at their code and did not understand this next part, but how to do this like normalization? So I think it's quite tricky, but like the algorithm which I know, because it's easy to, it would be easy to do that if the coefficients would be very small, because we can like incrementally fix everything by like we can easily, okay, if we had to add those two numbers, that would not be hard. But if we have to multiply them, like if we had to add two numbers with this cool property, it would not be hard, because it's some like simple left-right, greedy, maintain something, fix something. I think this task is quite popular. Whoever like solves the task like that. Nobody, okay. Yeah, okay, but when the coefficients are big, it gets tricky. So how do we deal with that? So I know a method which let's say that we can in a linear time add those two numbers, right? So like consider assuming this. So when we have bigger numbers, what we could do is let's have a recursive function sum a1 a2. Okay, so now I will do no, sorry, it's not sum. Sum. No, we'll have a recursive function fix a1, and we assume we have a function sum available. I'm gonna use the the vector notation, which does so multiplying a vector by a value means multiply every position and things. Okay, so what we do is we do that high is equal to fix a1 divided by 2 floor. Low is equal to a1 modulo 2, and we return sum low, sum high, high, right? And in that way, we by and also if it's empty, then return something, but whatever, right? So this fix always returns a fixed version. So this means that let's take all the let's divide all the coefficients by 2 and fix them, then add those two to each other to get the fixed version of a sum, and then add those low bits. And this works in an log range of the numbers. Okay, so next task will be maybe grid. Yeah.
So when you do this province, there will be some fractional coefficients, right? Because of the 1/5.
Yeah.
So how do you deal with that?
Okay. So.
Is it easy?
I mean, okay. What you can one way to do that is to pick two modulos because the coefficient we are convolving vectors of ones, so the coefficient will be at most what? At most n, right? I mean, if we convolve two vectors of n ones, then the coefficient at each position will be at most n, right? So we can do all the calculations modulo, and it will not hurt us. By that I mean, like the result that we will see there will be a real result, right? Okay, so like we can just pick a modulo where square root of 5 exists, and then just like calculate it naively, right? Or I think that maybe we don't even have to do a modulo here. If we are convolving, like if we are convolving vectors of ones and minus ones, then like the precision should be fine if we just calculate this on floats.
Okay. Yeah, but after doing the convolution of the polynomials with 1 and minus 1 coefficients, there will be also the 1 over 5 that we have left.
Yeah, sure.
And we should fix that somehow, right?
You
know, the coefficients will be integers.
Yes. So like you're saying that
it's about the fixed function. How does this
no, like this fixed function already, like what fixed function gets and outputs is a valid is a like description of a number as a sum of Fibonacci numbers, but those conditions do not necessarily hold.
Yeah, so the fixed function accepts only integer coefficients.
Yeah. I see. Okay, I think I see your question. So like your question is, how do we know that like the sum of those will be divisible like by 5 or something like that? I don't know. Let me think for a second. Okay, let's try to calculate this in some example. Can I erase it? Is this like part understandable? Okay. Okay, so let's do like t to the power of 3 minus t to the power of minus 3 by square root of 5 times t to the power of 5 minus t to the power of minus 5 by square root of 5. Okay, what happens here? We get t to the power of 8 plus no. Minus t to the power of 3 plus no.
You are multiplying two integers.
Huh?
You are multiplying two integers number. A Fibonacci number.
Right, so the answer should be an integer. So if the answer is something divided by 5, then the something is a multiple of 5.
Yeah, but the coefficients won't be individually. The coefficients won't be integers. The result will be an integer.
Right.
But
Yeah, like I think the doubt here is that, oh, but maybe it's just like the situation is that the coefficients are not necessarily divisible by 5, but like their sum weighted by those Fibonacci numbers is divisible by 5. So like the result is still an integer, yeah, and we are screwed.
Do you care about the result? Like, you just care which coefficients are there, right? Like.
Yes, like you do care. Wait, maybe I got this Binet's formula wrong. Let me check that.
Tá, vai dar um novo polinômio. Vocês também sabem que se avaliar esse novo polinômio e isso vai dar certo. Mesmo que não seja sei lá, não. Aí você vai pegar esse novo polinômio e esse polinômio. Aí tem que fazer aquele processo. Aí você tem que usar a propriedade Frank, I don't really understand this question because like we know that if we evaluate the polynomial that we have in that specific value of square root of 5 plus 1 divided by 2, if we evaluate it in this specific value and divide it by square root of 5, it magically is an integer. We do that by properties of Fibonacci. Because like what we are doing is we take one polynomial and multiply it with another polynomial. We get another polynomial that follows this property because we are both are Fibonacci numbers. And we are just rearranging the coefficients. Like it doesn't matter for us the coefficients themselves. We just know that if this polynomial is if the fixed polynomial is equivalent to the original polynomial, we know that for sure if we evaluate it on that specific value and divide it by square root of 5, it is an integer. Like it's okay. I think it's not required that the coefficients themselves are multiples of 5. I don't.
No, but like how the thing is, how do you then like output the good representation of this number, right?
But the good representation is just by fixing the polynomial that we have, right?
Yeah, but like to fix it, we need the coefficients to be integers.
No, we don't. The coefficients like we don't divide them. We don't have to divide them by anything. Because like what we have is like 1 multiplying because everyone it's like everything is scaled by square root of 5.
Okay.
Everything we either multiply it by 1 divided by square root of 5 or 0 divided by square root of 5. We don't have to do any division, do we?
Yeah, that's what I was trying to ask before. Like, if you just calculate that, ignoring the square root,
okay,
and then you calculate the coefficients, it will be the same as if you first multiply them and then rescale them.
Yeah, sure.
By dividing by 5. You can just ignore the square root of 5, and the result should be the same because it's not like within, like next to the t, it's just a constant factor. So like the square root of 5 really doesn't need to be in the calculation when you multiply the polynomial.
I don't think it fixes what I'm concerned about now.
But I didn't understand. You are trying to prove that this sum is a multiple of 5, like t to the power of 8 minus t to the power of 3,
yeah,
and the other 2. You're trying to prove.
No, I'm. Okay, so like, could you repeat your like solution or to that or yeah.
I mean, your number is a sum of that.
Yeah.
Like several copies of that. So you don't care about the square root of 5 because everything has it. So you can just factor it out. All the coefficients are integers because they either are there or not. So when you multiply a polynomial with just integers by a polynomial with just integers, the coefficients will be just integers. And then if you care about the result, you just divide by 5 again. But you don't care about the result because the coefficient will be already like a representation of the polynomial you wanted. So you just have to fix like half the polynomial. Like after you undo you ignore the part before the 0 with the negative exponents, and that will be already a representation in Fibonacci of the number you wanted. So you just fix that. Like you don't have to calculate the result.
Okay, yeah, you're right. Okay, I see. Yeah. So this works. I mean, sorry, we need to hurry a bit because we have half more hour and 4 more tasks. Okay. Okay, so the next task is grid. Okay, so in this task we had a grid graph and we had some number k, and we're asked to output a spanning tree of this graph such that the diameter of this spanning tree is exactly k. Okay, so basically we can like easily see that and the answer is at most like k should be less than n times m, and what's the like minimum number value of k we can do? It's is the one that maybe I should have a different color for that. Is the one that is achieved by doing something like that, or doing that in like another dimension. I mean, flipping this. And how do we get everything in between? So because for this guy, what we have to do is to do something like that. And okay, what do we do to like make this shorter? I mean, make a path a bit shorter. We can like put this edge instead of here, like shift it, and we can manipulate the length by like altering those other edges. And yeah, a little bit of casework, and that's it. Okay, sorry, but like there are a few more problems, so. Okay, so next problem is well. Okay, so in this problem we had some like we had some landscape and some number k. We could at most k times pick a position and decrease decrease the height of somewhere, and our target was to make a hole somewhere to the level 0 and minimize max over AI plus 1 minus AI absolute value. Okay, any questions to the statement? Okay, so when we have something like that, it's pretty clear that we want to binary search over this, and so let's have some guess. And now we are allowing the the difference between next two positions to be at most t. Okay, what do we do? So my first claim is that on this landscape we could run the following greedy. If there is a pair of positions where the difference is greater than t, then decrease the higher one. And my claim is that this greedy, because okay, let's say that we decided that the position should be here. So what would we do there? Then we would dig there down to 0, and then run this greedy till it's fixed, right? Basically, because if there are two positions and this is greater than t, then this won't get fixed by altering this. So we for sure need to decrease this guy. Any questions? Okay. So this greedy is of course not so fast because this k is big, those guys are big too. Okay, but my claim is also that even if you did not pick yet the position, we could run this greedy, and it won't break our further work, because we would have to do those fixes anyway, no matter where we dig. Okay, so how do we run this greedy? And this greedy gives us a helpful assumption that at the beginning the difference is at most t, which will help us later. Okay, so how do we simulate this greedy fast? So I know two greedies, one without proof, one with proof. So the one without proof is just go left to right and then right to left and fix the position we are currently in if it's required. I have no clue why it works, but there is a second one which consider every guy from the smallest value to the highest value and fix the neighbor if required. And this, I think it's clear why it works. Okay, so and now when we fix the landscape, so the distance is at most k, at most t between any two. Let's we need to check if it's possible to dig anywhere, and okay, so. My claim now is that let's pick a position where we dig, and now we will have to dig all of this, but here what we want to do is to dig t levels to the up, right? Is the optimal thing to do. Here we want to dig another t levels up. Okay, so how do we calculate where do we dig? So my claim is that if we have this fixed I position and we pick some j position, then we can check. Okay, I basically claim that it is monotonic. So for some prefix we will have to dig, and then later we won't have to dig anymore. Why? Because if there is a first position where we don't have to dig anymore, then the next position is at most the higher, right? Because of the greedy that we run at the beginning. So it's monotonic. And it's monotonic in like 2 ways, so in this side and in this side. So we can just do 2 pointers on that. And because also it is like somehow clear that for if a guy goes 1 to the right, then the like left border only moves to the right, right? And right border also moves only to the right. So we can do like a linear pass to check for every guy if we can actually dig there. Okay, any quick questions to that? Okay, so now art. Okay, so in this task we had 2 sequences, AI and BI, and the number k, and we had to pick exactly k times. Like on each position we had to pick either AI or BI, and exactly k times we were supposed to pick AI. Okay, and what we wanted to minimize is we wanted to minimize the maximum subsegment sum, right? In the sequence that we created. Okay, so when we want to minimize the maximum subsegment sum, it is also pretty clear that the and also n up to 100k. It is pretty clear that what we want to do is we want to binary search on this answer. So let's say we picked some t, which is now a bound for our sum. And what are we going to do? So the first thing that we can do is let's do some n squared dp first. So what we're gonna do? Let's say we have this sequence, and like we are somewhere here. So what do we really care about? We really care about how many times did we pick AI, right? And what's the sum? Like what's the biggest sum on S of x that's achievable? Because like this will be our worst enemy, and at some point it will like force us to choose something else that like to block us some possibilities. So now this DP is pretty straightforward because like DP and M is what? So basically we consider 2 possibilities, like we either pick AI and BI. If we pick AI, then like this goes to DP, so like DP n plus 1, sorry, so this is like DP n minus 1, m minus 1 plus AI max 0 and like we also need to check if this sum does not if this sum does not exceed our t, because like if this sum exceeds our t, then like we do not consider this case. And analogous thing for second guy.
But how do you know what's the sum?
What the sum of what?
Of the maximum suffix.
So like if at that point that was the best suffix, then I claim that after adding 1 value, it's either nothing or this suffix plus this guy.
I know, but how do you know what's that sum? Then you have to store it.
No, it's in a DP. Like this DP is the biggest sum.
It's already the answer.
So like that's the value that we store in the DP. And we want it, of course, to be as small as possible, right? This minimal sum. So we take like the minimum of those maximums. dp n minus 1 m plus bi 0.
Why is the 0? Why you can go near?
Because like no, I mean this sum is the best sum. So like we think about it that there is an enemy who picks this sum for us, right? And they can also always say, okay, let's make it empty now. It's 0, right? Okay. So okay, so this is our dp, and it's n squared, right? For every like guess. So we get n squared log n solution. Okay. So basically, what we wanna do now is we'll like think how does this dp look like? Okay. So my claim is that one column of a dp, like when we consider a column of a dp, it's always convex. And why? Because like you may think about it that it's inserting to a backpack elements, so like knapsack elements which have only sizes 0 and 1, and they have some values. And like one can by induction prove that such array is always convex. Okay, so and okay, so like maybe why is it always convex? So if it's inserting into an knapsack only values which are like which have sizes 0 or 1s, then if we have like size k, like if you want to check the element of like the result for a knapsack at sum of sizes equal k, we will always pick k best elements of size 1 and only the positive elements of size 0, right? And like the sum of the best k is like convex, right? It's just decreasing. Sorry, it's increasing, but it's convex, because otherwise, by convex I mean growing slower and slower. Because like we of course start from the best elements, so there will be like the elements later will be like less good, so they will increase by a smaller amount. Okay. So how can we store a convex knapsack? So convex knapsack can be stored by like maintaining the differences. I mean, we just we want to like maintain this set of elements that we inserted onto this knapsack, and this like. And also, I think some of positive ones. Sorry, some of. Okay. Sorry. So there is one more step that's needed here. Like for our implementation, what we'll do is like at first we'll say that we are always picking the better element, like the one which is smaller. So now that means that we picked too many of some element, right? Like it's either too many A's or too many B's. So now we think of it that we have to do like some like T switches, right, from A's to B's at some point. Okay, so what we now this like insertion from like the previous description of the insertion from the previous description to the next description of our column is like when we can pick element AI with size 0 or element BI of size with size element BI with size 1. Then what we actually say is we say, okay, AI is we add AI to the counter. I mean, let's say that like by default we pick AI, but we can also pick bi minus ai with weight 1, right? So now we just need to store those bi's minus ai's on some like sorted structure, which can be set. Yeah, and we will have this dp calculated that way. There was the tricky part here is also like how do we recover the answer, because we had to like print the construction here. So there are two ways. One way is to like write BST ourselves to do some rollbacks, like do one pass left right, and then like do rollbacks from this BST. But when you like maintain, it is actually possible to maintain like exactly what insertions did we do to our set and do rollbacks without writing our BST. Okay, 14 more minutes. So next problem. Okay, so oh, just one problem left. King's party. So in this problem, we had agreed. And we had some like zeros and ones. We had like some positions were selected and some were not. And we are interested in we consider a graph where two vertices are connected by an edge if they are in the same row or column and they store different values. And we have some initial state described by something, and then later we want to process updates which flip a single position, and the answer after each update is a maximum matching in this graph between like those ones and zeros. Any questions to a statement? Okay, so what we are doing here is so the first thing is that this is a biparic graph. So maximum matching is equal to minimum vertex cover, right? Who heard about it? Okay, it's Koenig's theorem. Okay, so max matching is equal to minimum vertex cover. So instead of max matching, we'll be calculating minimum vertex cover at every point. Okay, so what does minimum vertex cover mean here? It means that in every column we want to have either all the zeros or all the ones picked, and in every row we want also have either every ones or every one and every zero picked, right? Who like understands this? Okay, so why is it that? Because like when you look at one column, it's like all zeros are connected with all ones. So it means that like we either need to pick all of them for our like vertex cover or all of those for our vertex cover. Okay, so I'm gonna like just write a formulas from a tutorial because we have not so many time. Give me a second. Okay, so what we want to minimize is S equal to sum over ij Okay, so what does this expression mean? So for we define xi and yi yj as like sequence. So xi means if in ith row we decide to cover all ones, and yi it says if in yth column we decide to cover all ones. So like those like two sequences for row and column decide for us what choice do we wanna do there, and so then we can see that some single cell is not covered only if j is not equal to xi, which is equal to yj, right? They both need to be different, because like this means that in both column and row we need to decide to pick something else, to like pick the other category than this guy, for him not to be covered. So basically this sum, what it does, it's like uses products and stuff to write this, like sum over this, but like in a mathematical way. So then we can like simplify the sum by taking all the products and what we get is let's b equal to like sum aij, and c equal to like ci equal to sum over column, and the I equal to sum. This sum goes over I, and this over j. It's like we just define for something for a sum of everything, sum of columns, sum of like chosen row, and sum of chosen column. So this sum is then equal to okay, so what we can also see is that it doesn't matter for this graph if we like swap two columns in a grid or swap two rows in a grid, because like the graph is still isomorphic. So what we can see from this formula is that like we can imagine that both rows and columns are sorted such that like the number of ones in columns is decreasing, and the number of ones in rows is also decreasing. Right? We can do that by swaps. Okay, so basically. This means like by analyzing this formula further. So sorry for like skipping much. By analyzing this formula further, we will see that we always want to pick like we always want to pick some for those xi's and yi's. We want to pick like prefix of columns and prefix of rows, and like to be able to do that selection quick, we'll need to maintain a few segment trees. So we'll need to maintain a segment tree with with a sequences. Like we'll need to maintain A, but this is pretty easy. We need to also maintain like sequence C, sequence D, sorted C, sorted D, and and one more thing. Okay, maybe I will just send you the editorial of this problem. Okay, any questions to like any previous problems? We have 5 minutes.
I didn't get why is what did you calculate is?
So like S is a vertex cover. I mean, okay. So like, did you understand the transition from we are that like the maximum matching is equal to minimum vertex cover? Yeah. Yes. Okay. So now xi decides if in some column we pick all ones or all zeros, right? And yj decides for a column what do we pick, right? And now what I'm saying is that an element is not picked only when if it's column we decided to pick another type, and if it's and in its row we also decided to pick another type. Okay, and like this expression, what it does is it's a sum over all the positions. Did we take it? So like basically, this means okay. If this is 1, then it's good. If this is 0, then I want to add 1 only if. Sorry, should be. I think it should be like that. Yes, like if this is 1. No, wait a minute. If here we have a guy with 1, then so like if this guy is 0 and we picked both zeros, yeah. Maybe it should be 1 minus this. Okay, so what do we see now? If this guy is 0 and both those are 0, then what do we expect? No, then we want to add 1. So now, if this guy is 1 and they are both 0, then we want to add 0. Wait. If those two are equal, so if here we have, if we have at least 1, 1. Okay, I see now. So this says now that like if there is 1, 1 and 1, 0 among like those two elements, then this gets nullified and this gets nullified. So we add 1, no matter what the AI is, Because if there is like 1, 0 and 1, 1, then in either case, like this guy is covered, right? And if it's 0, 1, 1, if it's 0, 1, 1, then we subtract 1 here, because this guy is not covered, and this zeroes out. And if it's 1, 0, 0, then also we subtract 1, because this guy is not covered, right? So this expression just writes this summation. Okay. Sorry for a bit chaotic editorial today. I will send you the text editorial to that. Okay. And any further questions?
Frank.
Yeah.
I was going over the details of the previous tasks about the Fibonacci multiplication.
Yeah.
You mentioned that multiplying 2 palindrome polynomials would make a palindrome polynomial as a result, right?
Yeah.
But like the polynomials that we have, they're not exactly palindromes, right? They have like the same absolute value from the both halves, but one half is minus the other half, right?
Okay.
And we multiply both of them, we get like a real palindrome, like both halves are positive or negative.
Okay.
So we like the representation we have, we don't actually have the representation, it isn't represented by Binet's formula anymore. Like you don't have the same structure of a polynomial that one half the same of other half but negated. Like I didn't quite see how we were able to transform this representation that has both halves with equal sign to another representation where both halves have different sign.
Okay. Okay. Can I show you?
Yeah.
We don't have time on the whiteboard. Okay. Okay. So thank you. We'll answer your question.
Thank you.